давайте начинать. Мне был запрос переключиться на английский. Только, по крайней мере, один человек онлайн хочет, чтобы я говорил по-английски, я не могу отказать в этом случае. Вот. Но семинар, задавать вопрос по-русски, понятно, можно спросить по-русски. И семинар, видимо, пока человек не появится. Ну, я не вижу никого. Давайте, пока человек... А?
Включили, да? Спасибо.
Да, пока человек не появится на семинаре, семинар будет по-русски. Вот. Okay, so we switch to English. For me it's even better. One thing that I wanted to discuss from last class is maybe this difference between two different structures on R, smooth structures, which are not different as we figured out. If we think of different as not isomorphic, right? But there is this notion. So we had this manifold X, which is just R, and one atlas was this, right? The whole thing, and X, well, goes to X. And the other one is this. And in some books, smooth structure is defined as maximal atlas. It's atlas such that like all compatible chars are already there, right? So in this,
char это карта, да?
да. Yes. And so, in this sense, these are two different smooth structures, right? So if you throw into this all chars which are compatible with this one, meaning that the transition maps are smooth, then this will not be here. So with this notion, which we will never use because we don't really need this for anything. Like if you think of a smooth structure as some maximal atlas, that like you think about like all possible maps such that the transition maps are smooth, then this is different. But okay, we rather think of smooth manifolds up to isomorphism. So for us, they are the same. Okay, this is one thing that I wanted to clarify. And so, okay, let us continue. And the next thing that I wanted to discuss is what is a section. So sections of vector bundles. Вот про это, да? Ну, про то, что мы, как бы, в прошлый раз я сначала сказал, что вот у нас есть две разные гладкие структуры на R. Вот. А потом я сказал, что значит разные. Разные, это значит, что не изоморфные. Значит, это утверждение было неверно, потому что реально они изоморфны. Мы это показали.
Да,
да, это было сказано в прошлый раз. Я как бы пояснил, это утверждение имело бы смысл, если бы я разными гладкими структурами называл другое. Не изоморфные, а гладкая структура — это максимальный атлас. Максимальный гладкий атлас. Вот некоторые просто книжки так определяют. То есть,
наверное, можно сказать, что это не равные многообразие, но изоморфные. Ну, часто же такое, что у нас разные объекты.
Ну, это разные объекты, да, но как бы с точки зрения, да, они изоморфны, но как бы не равны.
Да.
Вот. Ну а что такое неравный тоже, как бы, ну я могу взять здесь как бы, там, не знаю, какой-нибудь x в 2x. Ну я таких могу придумывать, как бы, ну вот тогда это тривиальная вообще задача, да. Это тоже я хочу как бы сказать, что он равный, но в том смысле, что это как бы атлас, это как бы карта, которая, ну, отображение перехода будут гладкие вот с этим. Вот. И я таких карт сюда могу накидать, ну вот очень много. Вот. Могу вообще разбивать их на какие-то куски, там, и там где-то x, там где-то 2x, там где-то еще чего-то, как думаете, да? Но это все как бы одна и та же гладкая структура, в том смысле, что как бы максимальный атлас, вот, все карты, у которых значит, отображение перехода гладкие, у них один и тот же. Вот. Но вот этот карт там не сидит вот в том максимальном атласе. Вот здесь есть другой максимальный атлас. Вот. И в этом смысле они как бы разные. Вот.
А мы в курсе будем говорить, что они одинаковые замок.
Да, мы просто одинаковые нашли замок. Okay, for potential English listeners, we just discussed the same thing, but in English. Okay, so by definition, so if I have vector bundle, E over X, a vector bundle, and suppose that I have an open subset of E. So section on U is a smooth map by definition. From where to where? Well, F, so this is a definition. So this map is F, and this is from, by the way, this X I wanted to be, so this U I wanted to be open, of course, not in E, but in X. And then F is a map from U to E, such that if I take this map and compose it with projection, with pi, it gives me an identity on U. So F composed with pi is identity on U. Okay, so we have a projection, so we have a way how to go upstairs. That's the point.
Excuse me, bundle is the same as расслоение.
Да.
Хорошо.
Okay. Then some more terminology. Terminology or there's a thread. I don't know if people are okay with red. Looks like kind of ugly, but I don't know how to switch it. Try. No. Anyways, okay, let's. Oh, okay, it worked. Okay, so set of all sections is of course vector space, and we will denote it by S of U. So this is vector space of all sections on U, and well, this is just a terminology. If U is X, then the corresponding section is called global. Also, sections of the tangent bundle are called vector fields. And sections of cotangent bundle are called covector fields. Okay, and so actually, like all the sections over all open neighborhoods of X, they can be combined together in something which is called sheaf of sections. So maybe you will hear this word from time to time. Sheaf is пучок по-русски of sections. This is the following data. It's actually the same as contravariant functor. Well, from open subsets of X. Well, basically two vector spaces. So it kind of sends each open subset to well, sections on this subset, and it's a contravariant in the sense that, okay, on the subsets we have inclusion, so if I have V included in U, then, well, I have S of V, right? And so therefore I have restriction map from S of U to S of V. Okay, so we will denote this restriction, so res in which order? Okay, VU, like that. Because
Мне кажется, обычно обозначают UV, нет? Я обычно встречал обозначение UV. Ну, в общем, в другом порядке, но это, наверное, не принципиально.
это не принципиально, но я так хочу, чтобы композиция была в правильном порядке. Единственная моя мотивация так.
А шрифт по-русски пучок будет?
Да.
А там стрелка куда на самом деле?
Значит, вот это отсюда сюда. То есть, если у меня есть V, это подмножество, то это просто ограничение. Если у меня есть пучок, я его ограничиваю, у меня получается пучок на S от V. Сюда. Окей.
Have you already defined how this functor works? Where does it take the open subset of X? To where?
Two vector spaces.
To
So it's a sheaf of vector spaces, if you wish. So usually like you have sheaf of groups, sheaf of strings, whatever. So this is sheaf of vector spaces.
we have an object, open subset.
Yes.
The image of this subset is what?
A vector space.
Vector space.
Yes.
Can we see it somewhere in our bundle? No, yeah. It is in a vector bundle somewhere. Where is this vector space?
It's just a vector space. It's somewhere. It's not a subspace. It's just a vector space.
It is a sheaf that associates to vector bundles.
So it's a functor
This is
between
another object.
open subsets between the category of like this dumb category, but whatever, of open subsets of X, where morphisms have inclusions, and vector spaces where morphisms are linear maps.
So this is just.
This is just it.
we didn't
Nothing-
connect
nothing
it with
else.
The previous theory.
Yes.
Okay.
Okay, so now let's talk about more about sections of TX, about vector fields.
А вы недостаточно сказали, почему вы сказали, почему это предпочел.
Ну, да, я недостаточно сказал, но мне надо определить до конца, что такое пучок и так далее.
А как еще раз резвый угол определяется?
Это просто, ну, я беру, значит, у меня, что такое сечение, section сечения? Значит, это просто отображение с U в E, правильно? Но если V сидит в U, то это, как бы я его ограничиваю, это будет отображение из V в E. Вот и все. Okay. Anyways, we would like to see that actually vector fields are the same as derivations. Derivations of what? Of C infinity of X. Yeah, so I don't think if we have this notation, but this is just smooth functions on X. So what is a derivation? So if I have just by definition, if I have A, which is an associative algebra, then derivations of A, so these are all endomorphisms of A, well, that is maps from A to A such that L are linear, and it satisfies Leibniz rule. So D of AB is A DB plus D of A B. Yes. Let me change it. So this is L, of course. Sorry. And this is L, and then this is also L. Okay. So now. Yeah, so we will just denote vec, just notation. So notation. So vec x is just the same as well vector fields or global vector fields on x. So space of vector fields on X. And then we have proposition that we would like to prove real quick is that derivations, so there is a vector space as a morphism. Derivations of on C infinity of X is isomorphic to vector fields on X. So S vector spaces. Well, you don't have anything more than vector spaces here. Well, this one is well, this one is Lie algebra, but okay.
Вопрос. Векторное поле — это section на 3x, а пространство всех векторных полей это секшены всех по одному из 3x открытых.
Да. Ну, сейчас. Нет. Это все глобальные векторные поля. То есть с x в e. Со всего x. Окей.
Do we know something like, do they even exist? Okay, almost understand that they exist, but can you give a simple example of the global vector field of the some non-trivial space X?
Yes, there is an example, which is very kind of dumb example, and it's in one of your problems for today, which is just a zero section. But is this or you have?
Yeah, right.
Yeah, but this kind of explains more, right? Okay, so let's see. So we have proof. Right, so this should be a constructive isomorphism. So we need to construct. We will construct a map from where to where. Okay, let's do it. So first we can do it when x is just some like covered by just one by one chart. So okay, so fix some atlas A. Atlas, smooth atlas. On x of x, and then let me pick a chart. So this is chart. Okay. From So then I would like to build a map like this. I will call it row U, so construct. It's from vector fields on U to derivations on C infinity of U. So first do locally. All right. So I have my phi here, and so I can think of phi. So it is a map from U to Rn for some n, right? So phi of p, and we can, denote coordinates, corresponding coordinates x1, blah blah blah, xn. So this is just again notation. What are xi's? Okay. So now, what is TU? It's just by definition, because it's just covered by just one map. It's just U times Rn. Okay. And well, then, if I have a section V of TU, which is vector field on U, then it's actually a map, right, from U to Rn, because TU is like that. And well, we'll just introduce its components. So V1 of P, blah blah blah, Vn of P. Okay. And so then my goal is construct this, so I just
А вы не будете стрелять в У крест РН?
V будет стрелять в крест N, но как бы там всегда будет P.
А, ну в конкретной точке.
Ну, это как бы я как бы несколько, значит,
да.
себя веду фривольно с обозначениями, но вы правы.
Да.
А фи откуда?
Фи из U, значит, фи, соответственно, из U в N. Это просто карта на X.
V is a section.
V is a section, yes. So you're right that I should write here P, comma, a vector from Rn. But I will not do this because...
Я на самом деле не так вас просто понял. Все.
Okay. Okay, so now, no. Yes, I am going to just give you definition. Rho of U, it's clear what I would like. Rho of U of V, so, yes, I also need derivations, so maybe let me define it here. So define derivations which I will denote d over dxi. So this belong to derivations of t infinity of u, right? And they act on a function f from here as follows. It gives me another function, and this is just a d. So I just take df and then phi inverse of x1. Okay, maybe I need more space here. So let me start writing it over here. So this is derivation of the following thing. So I have to take f, then phi inverse, and then of what? x1 of p blah blah blah, and then I have x I of p plus t, and then blah 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 x n of p. And then I have to take derivative of this with respect to t. Okay, it's clear what it is. You just need to check that I don't have some mistakes. No, in writing.
Это не зависит от карты.
Не зависит от чего?
Ну, от карты, содержащей
Зависит. Потому что у меня иксы — это координаты, которые даются вот этим фи.
Should we restrict the last
Take t equals 0?
It's t to 0.
Yes, you're right. Yes, you're right. So take t equals 0. Yes. Okay. So now, yes, I define rho u of v is just as follows. It's just sum over I from 1 to n, vi of p. Well, I don't have any p here, so let's just write vi. And then d over dxi. So this is derivation in here, right? So it's just definition. So now I need to go from local to global, right? So now construct.
Excuse me, the sub index u in the P
it's from where phi goes.
Thank you.
Yeah, it's the first element of the chart. Is your coordinate neighborhood.
А то, что любая производная просто выглядит как очевидно, любая деривация.
Ну, это как бы не сложно, но мы покажем это в другую сторону. Да, хорошо. Значит, мы должны... Да, но пока что я ничего не утверждаю. У меня пока просто как бы векторное, линейное отображение туда. Все. Я не говорю, что оно там обратимо. Там. Значит, okay, so now construct this thing global, so grow from x to okay, so from vec x, yes, to dear c infinity x. And so if I have v from here, then, well, I need to see what is rho of v and how it acts on f, right? And so this is this is actually a function, this is from c infinity of x, so therefore I have to take it at some point p and see what's the value. So I just define it in the following way. I just take some u, right? I just take some u where p leaves this coordinate neighborhood. And just do this. So I just apply rho u. Okay, to where? To restriction from x to u of v, and then apply it to f restricted to u, and then take it at point p. So okay, this is my definition. Well, I just restricted to coordinate neighborhood and use my definition from here. That's it.
That's all perfectly clear.
Yes.
We know that.
Ну,
Yes.
нет, подождите, пожалуйста.
Yes. Okay. So now let's. So the question is why it doesn't depend on you. So it doesn't depend on you because how we define Tx and what is the clashing data between two coordinate neighborhoods u and u prime. So we just need to see that it's okay. Just quick check that doesn't depend. This definition doesn't depend on u. So suppose I have like u. So my p, suppose it lives in u and u prime.
А U из карты или любой открытый?
Это координатный, да, как?
А, координат.
Да, там, где у нас есть координаты. Okay, and u prime is also a coordinate neighborhood. One thing that I should write. So if my restriction, well, again, I'm using notation a little bit from x to u. V of p, so like this. Well, I'm abusing notation and think only about its value at Rn. So it's like just something like V1 of p, blah blah blah, Vn of p. Then if I restrict this to u prime, sorry, this I don't need, this I don't need, V of p. Well, then this is a claim, which is not hard to believe. It's just given as follows. So I have my G from U to U prime. So this is my clashing data. And this, like, okay, I have standard basis. So in standard basis, this becomes some matrix. Well, actually, yes. And so then I can write it like this: 1I VI, sum over I. Then this the same with 2 in here on the second place, and then we the last one is sum over I G U prime U 2I V I. So like that. And then not 2 but n here. Okay. And so if I do it like that, then I can just check that row of U prime of restriction of X to U prime of V. So I have this definition, right? So I substitute this with U prime, so I will have V primes in here and D over dx primes, and V primes expressed through V like this, right? And so therefore it will be like this: sum over J from 1 to n, and sum over I from 1 to n, and then I have G U prime U I, okay, J I V I D over dx J prime. And so I claim that this actually equals to sum over I V I D over dxi, just because this guy G U prime, so because G U prime U is G J I is dx J prime. It's just how we defined it over dxi. And so you just substitute and then get this. А? Когда определяли TX, мы говорили, мы определили с помощью коцикла. А коцикл определялся матрицей Коби переходом между координатами. Вот.
May I also ask you to clarify the notation? Why about two letters like sub-indices of restriction U and X? Why X is there? What does it mean?
So I restrict. So V is section of X, and I restrict it to either U or U prime.
So this is the restriction only for sections.
Yeah.
When the second index will be different? When we restrict, for example, a section over some another.
So this is different, right? So, no, this is not the. So okay, you're talking about this.
Yeah.
Yeah, from if you restrict from bigger to smaller. But yeah. Maybe, but this bigger is not X. Yeah. All right. So this is it. So the question is how to go the other direction from. So this is our map. Row we constructed. It doesn't depend on U. So how we can go backwards? So conversely, take some D, which is derivation of C infinity of X, and then, well, for each P in X, okay, we have a like coordinate neighborhood, right? So there exists UP open in X and phi P. So such that UP and phi P is a chart, right? So this is homeo to the Rn from UP. So this is homonym. Well, actually, diffeomorphism, right? Anyways, so the thing is that I'm skipping some technical details, but actually, if you have a map from some neighborhood to Rn, you can extend it to the whole X, such that it's such that they coincide on UP, right? So I claim that phi p can be extended to smooth map phi p bar from X to Rn. Okay, I leave it as it is. Well, there are different ways how to do it. But, okay, so this I just leave without proof. Okay, and so let me go forward. So my phi p bar of some q. This is just a definition of x's again. X1 of q, blah blah blah, xn of q. But q can live anywhere in x. Now, so this I need because my d is from. So because I have x, the whole x here. So that's the only reason. And so then I define a section of Tx as follows. So point P should go to, well, elements of this are triples up to equivalence. So it goes to a triple P, and then UP, and then okay. So I take my D, right? My section should depend on D. And so this is just this. So I take dx1 at P. So this is a vector. dx2 at P, and so on. And then dxn at P. Okay, so these are smooth functions, so I can apply d to the smooth function, take its value at P. So it's all well defined here. Well, this is actually well defined because I mean, I take this point and everything for this point, right? No ambiguity. The only thing to worry is that why it's smooth, right? And so, well, this is smooth because, well, if I take two close points, such that, say, Q is inside UP, right? I need to compare these two vectors, right, if they're close enough. Well, this is done by the following computation. Again, we need to use definition of Tx. What is the clutching data there? So check of smoothness. So if I take some q, then I have uq there, and then, well, I have some other coordinates corresponding to uq. I will mark them as x prime 1, x prime 2, and so on. So I will have this dx prime n of q, right? Okay. I need to take like a class of this triple, right? Actually. Right, so I take the class of this. And then I claim that this is equal to the following. So this the same Q should be here, but then inside UP, this vector becomes actually, and this is the claim, dx1 without prime, but at Q. Right. And blah 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 dxn of at Q.
А Q откуда?
Q из УП. То есть у нас есть P и Q. Вот. У P есть координатная, значит, координатная окрестность. И вот я беру точку Q, которая в этой окрестности живет, достаточно близко к P, короче. Вот. Я хочу пересчитать мое определение вот этой секции так, чтобы я мог сравнить, ну, насколько близко вот этот вектор к тому, который торчит из P. Вот. Я должен пересчитать его в терминах, значит, УП. Вот это утверждение, что он как бы пересчитывается вот так. Вот. Почему это так? Значит, ну здесь я, как бы, вот здесь используется, что D удовлетворяет правилу Лейбница. Okay, I need to switch to English again. Okay, so this is because, well, so I claim that dx, so this vector, so because this vector dxn, well, at Q, everybody, is equal to Jacobi matrix, right? So this is true if from this vector to this vector, from this to this, I go by Jacobi matrix, right? Because my clutching data is given by Jacobi matrix. So which is dx1, dx1 prime. Well, and I actually can choose my coordinates in such a way that, well, the Q corresponds to just 0. I always can, shift everything to 0. Right, and so blah 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 dx, what, 1 here, dx1 prime at 0, n prime at 0. So okay, here dx n over dx1 prime, and here dx n over dxn prime. And here I have the same but with primes. Dxn prime. Okay, so why is this true? This is true because, again, we have Leibniz rule. So my I can rewrite through xj. Just, okay, I'm thinking about xi as a smooth function in xj's, right? So I can consider Taylor series, corresponding Taylor series, and the linear term will be something like this: Cij xj prime. And linear term is actually given by this matrix. So C is actually this matrix, right? Well, this is, yeah, so this is 0. Just by definition, what is derivative is at the point is a linear term is in Taylor series decomposition, right? So therefore, and plus, well, something else. But about this something else, I don't care, because then if I apply D to both sides, right, and put x equals to 0, right? So in here, this will be some polynomials of degree greater than 2, right? So if I apply d, so I will have dxi equals to c some Cij dx j prime plus something, but this goes to 0 when x, if I put x equals to 0, right? Because of the Leibniz rule, I will always have here factors x, x I prime was for some I, right? Well, prime here goes to 0, which corresponds to my q. Okay, and so that's why this is true, and so that's why we can, switch from this guy to this guy, and then now inside the same UP, right? We compare these two, and of course these two vectors are close because dx is a smooth function, and that's it.
Так, а еще разложение x откуда берется?
Ну это просто изложение Тейлора по... Это гладкая функция. Вот. Я ее раскладываю в ряд по x штрихам. Ну как? У нас как бы... я всегда могу думать, что у меня есть линейно слагаемые, да, значит, коэффициент при линейном слагаемом это как раз и есть производные. Вот, а дальше все как бы будет какие-то слагаемые степени больше, чем 1. This proves that the other direction, right? So we use Leibniz rule to construct the smooth map. And the Leibniz rule we needed to check smoothness.
Excuse me, may I ask you to go on the previous slide, the right board?
Uh-huh.
Repeat in general terms the main idea of the proof of the second part. I'm a little bit lost.
Yeah, so I take D and I define a section. So I go backwards, right? So I take D, it's a some linear map here which satisfies Leibniz rule.
Mm-hmm.
Okay? So this is my definition. So I take a point, and to this point I put such a triple which is an element in here. So I need to go from x to tx.
Mm-hmm.
Here's the map for you. Okay, map is well defined actually, right? Because for each p, I chose kind of UP.
Mm-hmm.
Yes. Yes. And then I need to check smoothness. So how to check smoothness? Well, I take two cluster points, P and Q. So I need to compare two triples like that, for P and for Q. But for Q, I have different UQ and different X, which I denoted by X prime. So how do I compare if I have different UP and UQ? Well, I use my clutching data to go for Q to go to UP. And then I compare what's going on inside UP. So then I need to compare this guy and this guy. So they are close because dxi is a smooth map.
Mm-hmm. Thank you.
Yeah. Okay. Anyways, this is of course some basic stuff, but I don't think it's honest to skip it. It's kind of important to do it at least once in your life, and then okay. Anyways, let's proceed. Yes. We have some time. Do we? So we finished lecture at 11:20, right? Okay, so now now I'm going to talk about sections of Tx, okay, and these are called tangent bundle, tangent spaces, right? So for any x from x, well, Tx x, well, this is just a shorthand notation for a section, not a section, it's called fiber, right? So every pi inverse of x is denoted like this. This is the shorthand notation for that. So this is called tangent space. And well, tangent spaces are also isomorphic to derivations at a point, which is just basically the same thing as just derivations with a slight modification. So by definition, derivation at a point x of x is a linear map. Well, from C infinity now to R. So basically, we need just to take some derivation, then evaluate and call it derivation at the point, right? Such that, okay, let's call it somehow dp. Such that dp of fg is dpf g at, but this is not p, rather I should, so my point is x, right? So this is dx. G of x, and then, so this is x. And then f plus f of x, dx of g. And we have proposition that actually as vector spaces you have Txx is the same as derivations at a point, derivations at the point. Okay, let's just denote it like this. And it's proved just in a similar way. We proved this, so let's not repeat this. So proof similar to the previous proposition. Okay. Now all this I need to treat this as derivations at the point to introduce differential of a map. Okay, so differential of map. And then by definition, okay, so starting, so suppose that I have two smooth manifolds and smooth map between them, so f m to n, so it's smooth map. Then differential of f at some point p from n is a linear map well, it's denoted dpf, and this is from tpm to t f of p n, well, defined by so I need to take dpf, right, and apply it to some v, which is a vector in here. Right. So v is an element in here, and I think of it as a derivation at a point, right? So I take a derivation at the point p here, and map it to derivation at the point here, right? So derivation at the point is some function, and so this function would be h. So h is from c infinity of m. Okay, and the results should be just a number, right? Sorry, it's not true. It's not m here, right? But n. Yes. But v can map c infinity of m to r, but this guy should map c infinity of n to r. So I should feed it h, which is from c infinity of n. Okay, and this should give me a number, which I just define like this. So it's v acting on some. So v can eat something from c infinity of n, which is just, in this case, should be h composed with f. Right? So this is a function from m, from function on m, and v can act on this function and give me a number. Okay, so this is definition. Right. So we have the following kind of obvious proposition. But, well, kind of obvious. Maybe I'll skip the proof. So I have a map df. So this is a map from Tm to Tn. So the map like this. So how it's defined? Well, it's clear how to.
То есть мы можем представлять композицию HF в V же может принимать на вход гладкие функции на M, а это гладкая функция из M в N. Все еще.
Это гладкая функция на m. Сначала я m отправляю в n, а потом n я, значит, отправляю в r. Ну, собственно, с помощью h. H что делает? Это гладкая функция на n.
Все, да.
Да, так что вроде работает. Okay. So df works like this. So it takes pv, as I said, this is a pair, an element in M and then a vector in T PM, right? And then sends it to f of p, of course, and then dp f v. So the proposition just says that this is a homomorphism of vector bundles. Okay, I defined homomorphism of vector bundles last time over different bases, so that makes sense. Well, I don't know. Let's see if we can. So the proof is just straightforward. So you just need to do it in coordinates and see that in coordinates you basically have just all functions are smooth. It's a composition of linear functions and coordinates, functions which are smooth. Okay, so basically, so let's just skip it. So we just the only thing to check it is like accurately is smoothness. So proof is the only check. Then the only thing to check is smoothness, and this is done straight can be done in straightforward way. Okay. Right. So next thing that I'm going to define is a rank of a function. So definition. So if I have a smooth map again, then by definition rank of f at some point P is the rank of linear map, rank of DPF. DPF. That's it. So at different points, it's actually possible that I have well, different rank. Okay, so the next theorem is a very important theorem. Okay, let me go here. Okay, in English literature it's called the rank theorem. So theorem. The rank theorem. So suppose that I have M and N, two smooth manifolds, and suppose that I have a smooth map of constant rank, so smooth of constant rank, and let's denote this rank somehow R. And also let's denote dimensions of n to be n small and dimension of n to be n small. Then for any P from M, there exists smooth charts. Well, U, phi, and V psi of n and n respectively okay, I want P to be in here, of course. I want f of P to be in V, right? And so I also would like, of course, f of U to be inside V, such that f of U is inside V. What else? Yes. And also, so this this happens and the map f in coordinates, I will call it f hat. So this is just a composition of phi inverse and then f and then psi takes the form I just have, so it takes some coordinates x1 blah 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 and then xr and then xr plus 1 x, so dimension of m is m, and then this equals to so I just keep first r of them and then the rest is 0. So the total number of elements here is n. And of course, r cannot be bigger than n. Yes. So, okay, so we are not, so I will just say that, well, this theorem is not exactly about smooth manifolds, but rather about maps from Rm to Rn, right? So you can choose V, you just can choose U and V to be just, some open subsets inside, Rm and Rn. So again, I choose not to. So it's a kind of technical proof, but it's not so important. Like we will not learn anything about smooth manifolds, so I'll just skip it. So last year I spent decent amount of time on that, but I don't know. I think this is not a good choice. This was not a good choice. So okay, but this is an important theorem because like you can apply it in a lot of things. Just refer to it and everything becomes clear. Shall I start something new in 5 minutes? Okay, so I will just give the definitions. So by definition, so suppose that I have a smooth map, then f is called immersion if dpf is injective for any p from m.
А как по-русски immersion?
Погружение. Да. Okay. And F is called submersion. By the way, submersion I don't know.
Это всплытие.
Не знаю.
Субмерсия где-то переводит просто.
Просто субмерсия.
Okay. Submersion. So this thing people actually use, but in Russian I never encountered it. Submersion. If dpf is surjective for any p from m. Right. And injective immersion, so injective immersion which is homeomorphism. so homeo to the image is called an embedding. So embedding — вложение по-русски. Immersion — погружение, это вложение. Okay, and so we need this we need this to formulate what is a submanifold. Okay. So there are there are different types of submanifolds, and so this is like a subtle moment usually in differential geometry, what to call submanifold. And so we will encounter two of them, of submanifolds, two notions. First one is immersed submanifold, another one is embedded. So by definition, suppose that let M be smooth manifold, and N is just a subset of M. I don't even say that it has subset topology or anything. Well, it does, but it doesn't. It's not. It doesn't matter for me now. So, anyways, M is just subset of M, and suppose that N is smooth manifold itself. So N is smooth manifold. Itself. So what I want to stress is that not necessarily in the subspace topology. So not in subspace topology. Then N is called an immersed submanifold if if I well, inclusion map, so this is from N including, so this is inclusion map, is well, it's injective of course, but I need it to be immersion. Is an immersion. Yes. So if additionally I is homeo to the image, anyways, it's homeo to the image, meaning that N has subspace topology. Right, so that N is a manifold. It's manifold, which is given in the beginning. The corresponding topology is subset topology. So if additionally we have this, so basically I is embedding. Then N is called an embedded submanifold, and the embedded I put in parentheses because when I say submanifold without anything, I mean by default embedded submanifold. Okay. And so there is standard example of manifold which is immersed submanifold but not embedded. And this is just given by picture. So you have R2, and you can consider figure 6 or figure 8 like this. So it's open interval. It's an image of open interval from 0 to 1, say. Yes, it's mapped to R2, and so these ends, they go like infinitely close to this point, but never touch. So it is a manifold because of its manifold structure is inherited from the interval, but it's not the corresponding topology that is inherited from here. It's not subspace topology, because like if you like this point is a trouble, right? Yeah, and well, what is embedded is clear. You always can, draw a, find a neighborhood such that it looks like your sub manifold looks like a slice in this neighborhood. So this doesn't happen, for example, on this point here. But what I said right now is not like mathematically rigorous. This is some statement actually, which we will formulate next time.
Excuse me, this is the same as just is there an intersection in that point?
No, if there is an intersection, it's not a manifold. Well, you cannot put a manifold structure. Well, I mean, there is so the thing is you don't have double point. So if you consider like figure 8 curve, right? All points, like it has intersection, like technically, right? And all points will be inside your submanifold, right? So I'm just saying that this points is not like this map is injective, right? In this sense, there's no self-intersection here.
But what about the topology in the inner space? Do we have how does the neighborhood of that point look like?
Well, in subspace topology, so the thing is that you can consider this point here, and for example, this is an open interval. And if I map it, this goes to something like this. But this is never an open interval in subspace topology, because subspace topology means what? Means that I have to draw like an open neighborhood in R2 here and take everything which intersects with this open neighborhood. So I need to take in any open neighborhood of this point in subset topology, I always have to pick also some parts of these ends.
Yes, but
So I always will have to pick something from here.
do you state that the right space is as a manifold?
Well, this is manifold because 0, 1 is manifold.
The right one, the 8.
Погруженное, это не вложено.
Ну, право, короче, является многообразием гладким?
Является, да.
А какая реализующая окрестность у той точки, которая посередине?
Но она является не в топологии под многообразие. Ну ладно, давайте, значит, официально закончим лекцию. Если хотите, вы можете подойти и спрашивать. То есть там именно надо взять не окрестность точки вот в R2, а окрестность точки вот до того, как вы отобразили это в восьмерке.
Ну, так если у нас топология...
Топология, та, которая приходит из интервала.
Сейчас будет семинар, да?
Да.
У нас ведь топология у нас нет.
Да.
Да?
Она пришла из топологии отсюда.